Good morning, students. This is Latif sir. Today, in this video, I am going to start this second chapter of class 11th chemistry. The topic is language of chemistry. The topic is language of chemistry. In this chapter, in the basic introductory part, discovery of proton, discovery of electron, discovery of neutron, and Rutherford atomic model. These topics are given, but this topic we have already studied in class 9, and these topics are not important in class 11, and these are excluded from the syllabus also. That's why I'm starting from this point, this topic: dual nature of electromagnetic radiation. Dual nature of electromagnetic radiation. So first you have to know what are electromagnetic radiations. Electromagnetic radiations, in simple word, any type of lights are known as electromagnetic radiations. Okay, any type of lights are known as electromagnetic radiation, and these electromagnetic radiations has two components. One is electric field component and another is magnetic field component. That's why these are known as electromagnetic. Electro means electric field component and magnetic field component. So electromagnetic radiations are associated with two component. One is electric field component and magnetic field component, and any type of electromagnetic radiation propagates in the form of wave, and in and the component of electromagnetic radiation, the component that is electric field component and magnetic field component of any electromagnetic radiation always propagates in perpendicular direction. That is, if it is electric field component, then the magnetic field component will be perpendicular to the electric field component, like this. Okay, then if electric field component is this one, then magnetic field component will be perpendicular to this wave, like this. Okay. So any type of electromagnetic radiation propagates in the form of wave. So any type of light has wave nature, we know that, but here see the topic: dual behavior of electromagnetic radiation. According to this topic, this theory, light can have two type of property or two type of nature. One is particle nature, another is wave nature. One is particle nature, another is wave nature. So light has dual behavior. Whenever radiation interact with matter, in that case light display particle nature or particle property, and in some cases light act as wave. That is, to explain some properties or some phenomena of light, you have to consider light as a wave, and to explain some phenomena of light, you have to consider light as a particle. For example, to explain black body radiations, photoelectric effect, this phenomenon, you have to consider light as a particle, and to explain interference, diffraction, you have to assume light as a wave. Okay, so light has two component. Light has dual nature, that is wave nature and particle nature. Now see Planck quantum theory. In this theory, particle nature of light is taken. So in this theory, Planck quantum theory, it is in this theory it is assumed that light is a stream of small particle. Light is a stream of small particle or a small energy packet which are known as photon particles. Okay, and these photons are also called quantum. Okay, so according to Planck quantum theory, light is a stream of energy packet, energy wave, which are known as photon particle or quantum. Okay, and the radiant energy is emitted or absorbed is not continuously but discontinuously. That means when a body absorb or emit energy, it will be discontinuously always, not continuously. When a body absorb or emit real energy, it will be discontinuously. in the form of small discrete packet of energy which are known as quantum. And in case of light, these quantums are in case of light, the quantum of energy is known as photon. Now energy of each quantum is directly proportional to, according to Planck theory, energy of each quantum is directly proportional to frequency of light source, that is nu. If the frequency of light source is nu, then energy is proportional to nu. Or you can also write E is equal to h nu, where E is equal to h nu. Energy of each quantum is equal to h nu, where h is the constant which is known as Planck constant, and value of Planck constant in SI system is 6.626 into 10 to the minus 34 joule second, or in CGS unit the value of Planck constant h is 6.626 into 10 to the minus 27 arc second. Okay, so according to Planck theory, energy of each quantum or energy of each photon particle is directly proportional to frequency of the radiation or light. Okay, so according to Planck theory, you can write this equation: E is equal to h nu, where nu is the frequency of light or radiation and h is Planck constant. And second point, energy is always emitted or absorbed as integral multiple of this quantum. If a body release energy h nu, first time release energy h nu, then second time it will release multiple of h nu, that is n h nu. Suppose first time a body release 5 joule energy, first time a body release 5 joule energy, second time it will release multiple of 5, that is it may be 10, 15, 20, multiple, that is 2 times, 3 times, 4 times, or equal to 5. But not the like this, in second time it will not release energies like 6 joule, 7 joule, 8 joule. Okay, so energy will be energy absorbed or released will be discontinuous. Okay, and energy is always emitted or absorbed as an integral multiple of this quantum. So according to according to Planck theory, we can write E is equal to n into h nu, where n is 1, 2, 3, 4, this integer. Now see spectrum of hydrogen. Generally, you know that what is the spectrum. When you pass white light through a prism, then you will see that the 7 color of white light will be separated, and you will get a band of color, a series of band of color you will get in the screen. When you pass white light through a prism, if you pass white light through a prism, then you will get a band of different color of light. Okay, this is known as spectrum, and there are different type of spectrum, like absorption spectrum, emission spectrum, line spectrum, continuous spectrum, discontinuous spectrum, also known as line spectrum. And among these spectrum, line spectrum of hydrogen is important in this chapter. Okay, and you can read about the different types of spectrum, that is absorption spectrum, emission spectrum, you can read from your book. Okay, the most important part of the spectrum is line spectrum of hydrogen. Okay, so what is the line spectrum of hydrogen? When electric discharge is passed through hydrogen gas enclosed in a discharge tube. Suppose hydrogen gas is taken in a discharge tube, and electric discharge is passed through hydrogen gas taken in a discharge tube, and the emitted light and then the emitted light by the hydrogen gas from the discharge tube. If this emitted light is passed through a prism or spectrometer, the emitted light is analyzed by spectrometer. You will see that in the spectrum, in the screen, you will get different lines, series of different lines. Okay, so when electric discharge is passed through hydrogen gas enclosed in a discharge tube under low pressure, and the emitted light is analyzed by spectroscope, the spectrum consists of large number of lines which are grouped into different series. We will get a large number, different series of lines, okay, in the screen, and this is known as line spectrum of hydrogen gas. Okay, and on the basis of experimental observation, scientist Rydberg noted that all series of line in the hydrogen atom could be described by the following expression, that is, wave number of each line in the hydrogen spectrum can be calculated by this formula, that is wave number nu bar is equal to 109677. This value is known as Rydberg constant, which is represented by RH. Okay, so nu bar, that is wave number of the line in different series, can be calculated by this equation, that is nu bar is equal to 109677 into 1 by n1 square minus 1 by n2 square. Okay, where n1 and n2 are integer. So this is the atomic spectrum of hydrogen, and in the atomic spectrum of hydrogen you will get different Lyman series, different series, Lyman series, Balmer series, Paschen series, Brackett series, and Pfund series. These different series you will get in the atomic spectrum of hydrogen. Okay, and each series consists of different lines. Number of lines are present in each series. Okay, so this is atomic spectrum of hydrogen, and Lyman series is found in the ultraviolet region of light, and Balmer series is found in visible region of light. Brackett, Pfund, Paschen, and this series is found in the infrared region of light. Okay, now see what is the cause of this different series in the atomic spectrum of hydrogen. Okay, this is due to different type of electronic transition from defined energy state to defined energy state. For example, if electronic transition occur into the first cell, that is n is equal to 1, from higher energy cell, that is higher energy orbit, that is from n equal to 2, n equal to 3, n equal to 4. If electronic transition is occur to the first energy level from the higher energy level, then you will get Lyman series in the ultraviolet region of light. Okay, so in Lyman series, electronic transition is occur from higher energy cell or higher energy orbit to first orbit of hydrogen. Okay, in some hydrogen atom, it is found that electronic transition occur from higher energy level to n equal to second energy level, and you will get Balmer series. If electronic transition occur to second energy level from higher energy level, that is from third or fourth or fifth energy level or sixth energy level, you will get Balmer series. Okay, and when electronic transition occur from higher energy level to third energy level, then you will get Paschen series, like this Brackett, Pfund. Okay, so Rydberg in 1918 has given a simple theoretical equation for the calculation of wavelength and wave number of the spectral line. in different series of hydrogen spectrum, and this equation is known as Rydberg equation or Rydberg formula. Very important equation. You have to solve some numerical problem based on this equation. This is known as Rydberg equation. According to the using this equation, you can calculate the wavelength or wave number of the spectral line in different series of hydrogen spectrum. You can calculate the wavelength and wave number of the spectral line in different series of hydrogen spectrum, where lambda is the wavelength and nu bar is the wave number. Okay, and RH is Rydberg constant. RH is known as Rydberg constant, and value of RH is 109677 centimeter inverse. Okay, and N1 and N2 are integer, two integer, where if electronic transition is occur from N2 to N1, N2 energy level to first N2 energy level to N1 energy level, then you can write this formula: 1 by lambda, that is 1 by wavelength, is equal to nu bar, that is wave number, is equal to RH, that is Rydberg constant, into 1 by N1 square minus 1 by N2 square. Okay, where N1 electron transition occur from N2 energy level to N1 energy level. Okay, and this equation is valid for hydrogen atom only, and for other species, other atom, you have to introduce the atomic number, that is Z. So for other species, using this equation, this Rydberg equation, you can calculate the wavelength or wave number of the emitted light or spectral line in different series of that species. So the Rydberg equation becomes 1 by lambda is equal to nu bar is equal to R into Z square, where Z square is the atomic number of that element, that species, into 1 by N1 square minus 1 by N2 square. Okay, so this Rydberg equation is valid for hydrogen atom, and this is for other species. Here Z is atomic number of that element. Okay, and R is called Rydberg constant, and electronic transition is considered from N2 energy level to N1 energy level, where N2 is greater than N1, that is higher energy level to lower energy level or lower energy cell. Okay, so thus substituting the values of N1 and N2 in the above equation, wavelength and wave number of different spectral line can be calculated by using Rydberg equation. And now see spectral line for hydrogen. Name of series in Lyman series, value of N1 is 1 and value of N2 is 2, 3, 4, more than 1, that is 2, 3, 4, 5th, 6th. Okay, and Lyman series is found in UV region of light. Second type of series is Balmer series. In Balmer series, value of N1 is 2 and value of N2 is 3, 4, 5, 6, that is more than 2, and the spectral region is visible. In Paston series, the value of N1 is 3 and value of N2 is 4, 5, 6, more than 3. Okay, so and it is found in IR region. And Beckett series, in Beckett series, value of N1 is 4, value of N2 is 5, 6, 7, 8, like this, and it is found in IR region of light. In Phone series, the value of N1 is 5 and value of N2 is 6, 7, 8. Okay, like this, and it is also found in IR region. So you have to remember this table. Okay, from which energy level to which energy level electronic transition occurred. Okay, and corresponding name of this series you have to remember, and spectral region you have to remember, and some numerical problem you have to solve. You have to calculate wavelength, wave number of spectral line based on Rydberg equation. Now see Bohr atomic model. Next topic is Bohr atomic model. Niels Bohr in 1913 proposed a new model of atom on the basis of Planck quantum theory. The main points of this model are as follows. First point, in an atom, the electron revolves around the nucleus in certain definite circular path. Electron revolve around the nucleus in certain definite circular path, which are known as orbit. Okay, and each orbit is associated with second point, each orbit is associated with definite energy, and therefore these are known as energy level. Okay, each orbit is known as energy level or energy cell, and these are numbered as number n is equal to 1, n is equal to 2, n is equal to 3, like this, or k, l, m, n cell, like this. Okay, and next point, third point, only those energy orbits are permitted, only those energy orbit are permitted for the electron in which angular momentum of the electron is a whole number of h by 2 pi. That means, according to this point, only those circular orbit or circular cell are permitted in which electron can revolve, for which angular momentum means mvr, angular momentum, if mass of electron is m and velocity of electron is v and radius of the circular path is r, then angular momentum is mvr. According to this point, the angular momentum of the electron will be equal to h multiple of h by 2 pi, that is nh by 2 pi, where n is equal to 1 2 3 4. This n is known as principal quantum number. Okay, so only those energy orbits are permitted for the electron in which angular momentum of the electron is a whole number multiple of h by 2 pi. That is, you can write mvr is equal to nh by 2 pi. This is according to Bohr's atomic model, where m is the mass of electron, v is the velocity of revolving electron, r is the radius of the orbit, h is Planck constant, and n is an integer. And next point, point number 4 of Bohr atomic model, as long as electron present in a particular orbit, it neither absorbs nor loses any energy, and its energy therefore remain constant. As long as electron is present in a particular orbit, as long as an electron is present in a particular orbit, it neither absorbs nor loses any energy. Okay, that means energy therefore remain constant in a particular orbit or particular energy level. And next point, point number 5, when energy is supplied to an electron, it absorbs energy only a fixed amount as quanta and jump to higher energy level. Okay, so when energy is absorbed by an electron, when energy is absorbed by electron, the electron will jump into higher energy level. Okay, when energy is absorbed by an electron, the electron will jump into the higher energy level. Okay, so when energy is supplied to an electron, it absorbs energy only a fixed amount as quanta and jumps to higher energy state away from the nucleus, known as excited state. And the excited state is unstable. The electron may jump back, this electron may jump back into lower energy level, may jump back into lower energy state by releasing energy, by emitting energy, same amount of energy. And the energy difference between these two energy level, which is written as delta is equal to E2 minus E1. Suppose energy of this cell is E1 and energy of this cell is E2, then the energy difference is delta E is equal to E2 minus E1, which is equal to energy absorbed by the electron, that is h nu. Okay, now see achievement of Bohr atomic model. there are some achievements of Bohr atomic model. Bohr atomic theory has explained the stability of an atom, has explained the stability of an atom. Second point, second achievement, Bohr's theory has helped in the calculation of energy of electron, velocity of an electron, and radius of this stationary orbit in hydrogen atom and in one electron species. So Bohr atomic theory, Bohr atomic model is valid for one electron system like hydrogen atom. Okay, so in hydrogen atom and one electron system like lithium 2 plus and helium plus, these are one electron system, and hydrogen and Bohr atomic model is also applicable for these ions which are single electron system, H plus, Li plus, He plus, Li2 plus, He plus, okay, Be2 B3 plus. For this single electronic system, Bohr atomic model is also applicable. Now using Bohr atomic model, you can calculate the energy of electron in nth energy level, in energy state or nth cell. Okay, and the mathematical expression for energy of an electron, the mathematical expression for the energy of an electron in the nth orbit or nth cell is En is equal to 2 pi square mz square e to the power 4 by n square h square. This is the formula of calculation of energy in nth orbit. En is equal to minus 2 pi square me means mass of electron, z square, z means atomic number of the element, and if the atom is hydrogen, then value of z is equal to 1, and E is the charge of electron. Okay, and n is the energy cell, energy level, nth energy level, and h is Planck constant. So En is equal to minus 2 pi square me z square e to the power 4 divided by n square h square. Using this formula, you can calculate energy of an electron in nth Bohr orbit. And you know 2 pi mass of electron, that is me, and charge of electron, that is E, and Planck constant h, all these quantities are constant. All these are constant value. For mass of electron, you know mass of electron is mass of electron me is 9.1 into 10 to the minus 31 kg. Okay, similarly charge of electron is 1.6 into 10 to the minus 19 coulomb. Planck constant is 6.627 into 10 to the minus 34 joule second. So inserting the values of this constant, we obtain the value En is equal to 2.187 into 2.187 into 10 to the minus 18 into z square. As z and n, these are two variables and others are constant, and after putting the values of this constant quantity, you get the energy En is equal to minus 2.178 into 10 to the minus 18 into z square by n square, joule per atom. Okay, and in kilojoule per mole it is 1312 into z square by n square. In kilojoule per mole, the value of En is equal to minus 1312 into z square by n square kilojoule per mole. And for hydrogen atom, just you have to put the value z is equal to 1. So En, energy of electron in nth orbit of hydrogen atom, is equal to 2.178 into 10 to the minus 18 into 1 square into z square means into 1 square divided by n square. It is in joule per atom unit. And in kilojoule per atom, the energy of an electron in the nth orbit of hydrogen is En is equal to minus 1312 into 1312 by n square kilojoule per mole. It is in kilojoule per mole unit. Now see, using Bohr atomic theory, you can calculate the radius of circular orbit. Like calculation of energy, there is a formula Using this formula, we can calculate radius of this electronic path, and the formula is radius of nth orbit Rn, radius of nth Bohr orbit Rn is equal to n square h square divided by 4 pi square me that is mass of electron into z square, where z is atomic number of the element and E is the charge of electron and me is the mass of electron. And after putting the values of the constant, that is after putting the value of Planck constant, value of 4 pi square, mass of electron and charge of electron, charge of electron is 1.6 into 10 to the minus 19 coulomb, mass of electron is 9.1 into 10 to the minus 31 kg. After putting this value, we get the value of radius of nth Bohr orbit of hydrogen, which is Rn is equal to n square by z into 5.2921 into 10 to the minus 11 meter. 5.29 into 10 to the minus 11 meter. Okay, and for hydrogen you have to put the value of z as 1. So for hydrogen atom, the radius of nth Bohr orbit Rn for hydrogen atom is equal to n square into 5.29 to 1 into 10 to the minus 11 meter. Okay, you can express this value in angstrom also. Okay, and the radius of first Bohr orbit, that is r1, in the hydrogen atom is the radius of first Bohr orbit, that is for the calculation of radius of first Bohr orbit, that is you have to put the value of n is equal to 1, that means first Bohr orbit, and the radius of first Bohr orbit is 5.29 into 10 to the minus 11 meter. Okay, and which is generally written as a0. A0 is equal to 5.29 into 10 to the minus 11 meter. Okay, or you can also write 0.529 angstrom. So a0 is the radius of first Bohr orbit. So you can write radius of nth Bohr orbit for hydrogen atom Rnh is equal to radius n square into radius of first Bohr orbit. You can also write this equation. Now see calculation of velocity of an electron using Bohr atomic model. The formula is Vn, the mathematical formula is Vn, that is velocity of an electron in nth Bohr orbit is equal to Vn is equal to 2 pi z square by nh, 2 pi z square by nh. And after inserting the constant values, like inserting the value of 2 pi e and h, we get the relation Vn, velocity of electron in nth Bohr orbit, is equal to z by n into 2.18769 into 10 to the 6 meter per second. Okay, and for hydrogen atom you have to put the value of z as 1. So we get Vn, velocity of an electron in nth orbit of hydrogen, is equal to 2.18769 into 10 to the 6 meter per second divided by n. You have to remember these formulas. Some small numerical problem you have to solve based on this equation. Okay, and Bohr theory has explained third achievement of Bohr theory. Bohr theory has explained the atomic spectrum of hydrogen atom. Okay, now see limitation of Bohr atomic model. There are some limitations also. Bohr atomic theory cannot explain the atomic spectra of the atom containing more than one electron. I have told that Bohr atomic theory is applicable for for one electron system, but it is not applicable for system having more than one electron, that is in multi-electron atoms. So the theory could not explain the atomic spectra of atom containing more than one electron or multiple electron atoms. Second, Bohr theory failed to explain the structure of the spectral line, fine structure. It failed to explain the finer structure of spectral line. You can explain normal atomic spectrum of hydrogen by using Bohr atomic theory, but final line spectrum of final line structure of spectral line cannot be explained by Bohr theory. Next point, Bohr theory could not offer any satisfactory explanation on Zeeman effect or Stark effect. And fourth point, Bohr theory failed to explain the ability of atom to form molecules formed by chemical bond, and it was not in accordance with Heisenberg uncertainty principle. These are limitations of Bohr atomic theory. Okay, now see reasons for Bohr atomic model. Reasons for failure of Bohr atomic model. There are many reasons. First one is the wave character of electron is not considered in Bohr atomic model. The wave character of electron is not considered in Bohr atomic model, and according to Bohr atomic model, an orbit is clearly defined path, and this path is completely defined only if both position of velocity of electron are known exactly at the same time. But this is not possible according to Heisenberg uncertainty principle. So these are two reasons for the failure of Bohr atomic model. Okay, thank you students. Again, I will continue this discussion on this chapter in the next video.